Here's another example. This time we will listen to something, so we will have an example with sound. And in this example, we have a sampling rate of 8 kilohertz, and we want to build a bandpass filter. So for this filter, our low stop band will be between 0 and 0.0.5, our pass band between 0.1 and 0.2, and our high stop band will be between 0.3 and 0.5. So here again we have 0.5 as the Nyquist frequency and 1 as the sampling frequency. So our pass band will be in between 0.1 times 8 kilohertz, so 800 hertz, and 0.2 times 8,000 hertz, which is 1.6 kilohertz. So here we are defining our factor for bands. So there's 0 and 0.05, 0.1 and 0.2, 0.3 and 0.5. So we're defining our low stop band, our pass band, and our high stop band. So this we can also have the desired magnitude per band, and here we have, for example, 0, 1 and 0. So 0 for the low stop band, 1 for the pass band, and 0 for the high stop band. And we choose our weights. So here we're choosing 100 for the low stop band, 1 for the pass band, and 100 for the high stop band. And in this case, the number of taps n equals to 32. So this is the filter length. So again, we're defining here our filter. So we are using the Remes algorithm, using the SciPy signal Remes function. So we're importing NumPy, SciPy signal, matplotlib. This we are defining the length of our filter, the number of taps. Here we are defining our filter. So this is the bandpass filters. So we are passing all the parameters that are necessary. And here we are plotting the frequency response using the FracZ function from SciPy signal like we did previously. And this is the magnitude of the frequency response of our bandpass filters. So here, as you can see, I didn't use that matplotlib trick, so it's giving me from 0 to 3.14. So this is pi, and we could also apply the same thing what we did before and have here multiples of pi if we would like to do that. So again, here it is the normalized frequency, where pi is the Nyquist frequency. So observe that the equiripple behavior inside each band. We see our pass band a little to the left of the center. The side lobe to its right is from the transition band there. So this is our pass band, and we have low stop band, high stop band, and we can also plot the impulse response. So this was just the B pass here, is the impulse response. So when we plot here, this is the impulse response of our bandpass here, and we can see that the impulse response is symmetric around the center because it's a linear phase filter, and it still has a similarity with a sinc function.